Okay, then we get into part 3 for your unit 9, and we're going to deal with plastics, your polymer composite, or plastic composite, the same thing. So polymer matrix composite, your PMC, but then for some reason we don't use the PMC outside, okay, and you will sometimes see in the documentation, but for polymer composite we say like a plastic composite for the common, alright, common words. So they consist of matrix and reinforcement, same as all other composites, yeah. So the matrix here for the plastic is a glue. It's going to bond the fibers or whiskers or particulate again together to form the composite, so your review, general review for your composite. And then polymer again are the most widely used matrix materials, right, for composite. So again, we are in the age of plastic, okay, plastic era. So let's go to the next one. Thermoplastic polymer matrices. So every time you think about plastic, we have two different plastic. One is a thermoplastic and the other one is thermoset. So we have two different matrices as well to make two different plastic composites. Yeah. Of course, there are so many subtypes. So this type of composite is enhanced or filled polymer, and we use these composites in conventional thermoplastics, like high performance thermoplastics, alright? So both of them we use in these, okay, composites. So again, don't forget we have two parts, your matrix part and your reinforcement in the composite. And we're not talking about matrix part. And in matrix part we have two plastic going on. The very first one that we're going to learn is your thermoplastic. And in the thermoplastic, we have two things going on again. So you have conventional thermoplastic and then high performance thermoplastic. Okay, so in your memory, you gotta start with the like that. So in order to make the composite, yeah, I need matrix, and then I need reinforcement. So here for the plastic polymer, we're dealing with a two plastic. So the very first one is a thermoplastic, okay, matrix. And thermoplastic matrix, okay, so thermoplastic matrix, TPM, thermoplastic matrix, we have two, okay. One is a conventional, okay, thermoplastic, and the other one is better than the conventional, so therefore high temperature or high performance. So high performance, they can stand a really elevated temperature because they're pretty good plastic type. Okay. Alright. And that's all you have to put into your head, yeah? So it's easier to remember that way than this. So try to practice writing like that. So when you close your eyes and picture thermoplastic polymer material, you can see that, yeah? And you can be able to just write it that way. Okay, I'm going to go ahead and erase it, trying to teach you how to put into the head, because I see based on the first test, you're having an issue of retaining the information in the head. So try to practice to put in and take it out, okay? Alright, so conventional thermoplastic composites are used for gears, structures, and other industrial applications. And the thermoplastic use is detected by, again, characteristics associated with the resin. What is a resin? Resin is your plastic material, okay? We're dealing with, again, matrix part of the composite. And in there, we're dealing with the thermoplastic, and this one is the first one, conventional one, yeah? No, the high performance one. So these characteristics may include cost, environmental resistance, processability, coefficient of friction, resistance to creep, and then all others desired, okay? Properties that you want. So here are the example picture of your conventional thermoplastic. High performance thermoplastic, see how strong they look. So these composites, they have short processing time, severe damage tolerance, Superior damage tolerance is nothing but it has ability. So these materials have ability to function, okay, adequately after a flaw has been introduced. So even if they have a damage or injury, they can function, okay, without changing their property. So they can resist to flaw or damage. So advocates a solvent resistant, low manufacturing cost, it's cheap, yeah, high fracture toughness, impact resistant, good resistance for cracking, and the easy quality control. So those are all your advantages for high performance thermoplastic. Disadvantage, difficult in maintaining high quality prepreg, and we're going to talk about prepreg later. And cost of tooling, right, at a high temperature. Even if it is, where's my here? Even if it has a low manufacturing cost, when you want to deal with a high temperature, you have to put more money for tooling. Okay, so indeterminate fatigue. So you can predict the stress in the composite made from the high performance thermoplastic, and also the creep behavior. Even though we generalize, okay, that it is. It can, okay, resist to both of them. So here you have your impact resistance, but then sometimes it can be unpredictable. Okay, so anyway, so let's go to the next slide. So then we get into the second type of plastic, and that's your thermoset. We're still in the matrix parts. Okay, we're not even getting into the reinforcement yet. So for matrix thermoset, we use polyester, epoxy, polyimide, and phenolic polymers. Okay, so these are the commonly used matrices for plastic composite. So they are matrix for all commercially advanced composite. This one is a resin bath right there. So you can see the thermoset resins in the resin bath. So they account about 80% of all reinforced plastics. Okay. So that's a pretty popular type of matrix. Polyester resin. So commercial fiberglass discount reinforced composites are made from polyester resin. Resin is just a plastic, okay? And this plastic is your polyester in your thermoset. So they're low-cost matrices and can be used in a variety of processes to make the composite. And they're not used in making or advanced composite. Why? Because they have lower temperature capability, lower weather resistance, and lower physical properties. Because of all that, we're not using in advanced composites. Okay. Cross-linking. So this is a review for your polymerization. So cross-linking of your thermoset polyester resin for the thermoset matrices to make polymer composites. So when you go back to the polymerization, and that's how we play with the internal structure, okay, internal structure to enhance the characteristic of the composite made from these plastics. So starting agent, the same thing, you have an initiator, and it can be a styrene, okay, and then it's going to begin the reaction. And then reacts with the polyester chain, the same thing. It's a typical polymerization reaction. Start with a styrene initiator and then going to react with a chain, and then going to produce all the cross links, right? So the entire reaction, we call that outside. That's for the outside manufacturing process. We call that curing. Inside, this is what's going on, okay? Structural. So try to pay attention which level you're talking about, molecular level, and that's our level. So styrene serves as a cross link between molecules of polymer. So an inhibitor, again, you can't just let it go, the reaction. You have to control the reaction. Every time we try to control the reaction, okay, we use an inhibitor. So that's a control for polymerization reaction, and we're going to add that or throw it in, yeah, to the mixture. So what it does is going to prevent the spontaneous cross-linking. We don't want spontaneous. We don't want it to be chaotic. We want it to go in a systematic way, okay? So that cross-linking by the resin mixture, we will use the inhibitor to cross-link systematically in a correct way, okay? But then sometimes you can't control your own inhibitor, okay, because even if we try everything we can, and sometimes the imperfection happen, so errors happen, and you're going to have the resins is going to eventually cross-link anyway, okay? But of course not as chaotic as without the inhibitor, yeah? So a resin system is going to store the mix, okay, store and mix the polyester resins, your curing agent, and you have your fillers, and then your inhibitors all together, yeah? And then, of course, every time you store something, you have to control the temperature. So the temperature of that container, we're going to raise it when we cure, okay? Initiator, we're going to store in a different container because initiator can stop that process. So therefore, you never mix the initiator along with all other, okay, ingredients in that polymerization. Cross-linking, continue. So commercial polyester resins, they have limited lifespan. So we're gonna take a look at two life. The very first one is your shelf life or storage life, and the second one is your pot life. The shelf life or storage life is just we're looking at the amount of time an unmixed resin can be stored before cross-linking can happen. So you have your initiator to start the polymerization reaction, but then when you are storing these ingredients in your storage system, we're counting that time. Okay, so that time, so we said the amount of time and unmixed resin. Okay, you can store that resin before you mix them. Okay, so that need to be a particular amount of time because you can hold the unmixed resin forever. Yeah, so it definitely has a shelf life or storage life. Okay, the time that this resin can be good. Yeah, because it can go bad. So therefore, you have to find the amount of time for each type of resin. Okay. So even though we're studying the thermoset, you still have a different kinds of thermoset, okay? Plastic. So it depends on the type of the resin, the shelf life or the storage life, they vary. Pot life is amount of time. Now we're measuring the time again, a resin can be stored after the initiator is added, okay? So you have your container right there and then polymerization, okay? So before you add the initiator, it's outside, okay? And you have one shelf life. And then you add the initiator. So now my initiator is inside of my system, resin system, okay? Here is all other stuff. Then you have a pot life, yeah? So that's the initiator out, initiator in. And if initiator is inside of your resin system for reaction, called the pot life. And you're going to time it in time, okay, the shelf life when the initiator is outside, okay. Here, of course, we're not using initiator here because you're using the cross-linking. Cross-linking is already indication that the initiator presence inside of that resin mix. All right, so when curing rate is too slow, accelerators are added to expedite the curing process. Sometimes you're going to take a look at the polymerization reaction and you're going to check the standard speed, okay, of that reaction. And if the curing or the reaction rate is low, okay, you're going to add the accelerator, your catalyst, yeah, accelerators. And you're going to expedite the curing process. So the typical accelerators are your cobalt, naphthalate, and diethyl aniline, and dimethyl aniline. Okay, so these are the typical accelerators that we use for thermoset polyester resins. This guy is actually, what is this? This is a cobalt because the color is really purple, yeah, blue purplish. Epoxy resins, another thermoset resin. So these resins are used for nearly all demanding structural applications, like your aircraft, your aerospace structures, printed circuit boards, right? These are micro, these are macro products. So this is because these resins, they have like excellent adhesion, high strength, low shrinkage, corrosion resistance, and process stability. Okay, so the types, when you look at it, we have conventional epoxy resin and we have a high toughness epoxy resin. So don't forget your flow chart. Okay, we come from a composite made of matrix and reinforcement. We're now studying matrix. We studied the thermoplastic, 2 of them, and then we're now in Thermoset. Thermoset, we finish with the polyester, and we come into epoxy resin. And epoxy, we have conventional epoxy, and then we have high tough epoxy. So put some effort and use some papers, and use some pencils or pens, and then draw these flow charts, okay, to study them. Okay, prepreg. So prepregs are nothing but the fabrics like that, saturated with resins called plastic. Okay, so prepregs can be produced using epoxy and curing system that do not react at freezer temperature, meaning like cold temperature, but it can be cured quickly at high temperature. Okay, cure is just a reaction, by the way. So high performance aircraft application frequently use a prepreg. They very much look like the fabric material, but then made of plastic. So polyimide looks like a little sheets like that, and these resins are really expensive, and because it's cost, we use it in only for certain applications. So they're not widely used. So they're prepared when optimum thermal stability, high temperature is required. So every time you have to do with the high temperature, the process is expensive, because now we're also looking for the optimum stability at that temperature, and that's pretty difficult to do. So everything that is difficult in the manufacturing operation, there's money behind it. Yeah. So they are primarily used in aerospace applications. Because for aerospace, so we're going out of the earth, so you gotta make sure your product is strong enough to be in the space environment. Okay, where it has incredible amount of how can I say, forces right in there, and also need to float, okay, and move, and with so many hanging objects all around it, okay, big giant objects all around it. So these resins are formed by condensation, polymerization, not the regular, the other one. Yeah, don't forget your condensation polymerization is different from regular polymerization reaction. Okay, I'm going to ask you in an exam. That's one of the textbook question. So with a longer processing time than other resins. Okay. Phenolic. So these resins, they have limited, but phenolic resin we use in important applications. So principal applications for phenolics we use in rocket engine nozzles, nose cones, high temperature aircraft ducts, and muffler repair kits. Okay. So why do we have to put incredible amount of money for space projects like that? Is because we want to the ultimate goal is the continuation of the human species, because all of us have already realized that the earth is not going to stay forever. Okay, just like we grow old, the earth grows old, and one day it's going to disappear somehow. Yeah, and the condition around the earth, which is your atmosphere and everything we have on it, it's going to change. Yeah, so that change environment, we are not quite sure it's going to support the sustainability of our species. Okay, because our species live in a very limited condition, like we need a certain temperature to survive. So for all that, we throw objects into the space and usually take pictures and videos and send the data back to the world to be able to understand, okay, what's going on out there, and if there's a possibility that we can we can use one of the objects out there to live, yeah, continue. Or if you can at least to simulate or induce the atmosphere or something like on Earth, yeah, for us. So what are those? So let's go next one, the manufacturing. So how are we going to manufacture the plastic composite? We're going to use all this. So the very first one is manual layup and prepreg. Second one is a vegan bagging method, filament winding, autoclave method, and pultrusion, compression molding, injection molding, and your resin transfer molding. We already studied all of that, and we're going to pay attention to this. Okay, so the very first method is a manual layup. So you can see how people do it with a hand, yeah. And prepreg, you already know, is fabric. So it's a simple technique called layup or layup molding. So you're gonna lay things up, yeah. So that is the first technique to make the modern plastic composite. So fabric or mat is saturated with a liquid resin, and the layers are placed on the shaped surface. Right here is your surface or mold by hand. All right, desired thickness is obtained. So pressure is applied to remove the trapped air. So it's kind of like push the air out, yeah, on the surface. So the product is then allowed to set or cured. So layup can be used with your prepreg fabric to overcome difficulty in handling resin and fiber and to achieve the better quality control of the finished product. Because without the prepreg, you can't be able to get really good finished products. Vegan backing, you're gonna apply the vegan to layup, right, to the layup to help compress that layers, so it goes faster. So the process is required for prepreg fabric layup and then helpful to manual layup. Okay, this is just exaggerated a cartoon diagram that you can see what we do here with the vegan controls right there. So this process press the composite layers together and withdraw the excess volatile. So that's really important here, you know, to get rid of. It's kind of like just get rid of the trapped air, right, from the layers, just like that. And volatiles, okay, are the residue solvents, unwanted material, and reactive resin, and your trapped air. Okay, so we're gonna get all of that out by using the vegan bagging. Here is a textbook diagram, and this is just a typical vegan bag assembly. So that's where I'm showing you with that cartoon picture. That's your vegan line, vegan valve is right here. Your sealant is right here. Okay, here this is your bagging film, and your breather, your barrier, your bleeder, your release, your part, and your tool. Okay, and that's the mold right there. And you're molding according to that. And press it out. Press all your volatiles out. Filament winding. So this method is there's a continuous tape, right, of resin saturated fibers, and it's rubbed over a foam to create the part. So successive layers are added at the same or different winding angles until the angles are made by the machines like that until the required thickness is reached. So it is like an automated layup machine. Okay, so we start with a manual layup and then we vacuum back, and then here we're using the machine. Okay, automated layup machine. So it does not use a pre-preg like in the manual layup. So this process, what it does, it saturates the fibers using the resin bath and called the wet filament winding, or simply wet winding. Okay. So if you think about the filament winding, you have to understand that we're using the resin bath, right? That's the reason why we call it the wet winding or wet filament winding to create the part. Yeah. And here is your diagram from your textbook, just showing you the continuous type of resin saturated fiber, and it's wrapped over the mandrel to form a part. Okay, so here you can see your spools right there, filament carriage right here, your resin right in here. Yeah, and this is what you just saw in your previous slide with the regular picture. This one is just a diagram, and here's your mandrel and your helical winding, and your hook winding is going on right here, and that's your motor. Your machine is going to drive your automation, okay? And you're going to feed the filament right here, going that direction, yeah. Autoclave curing or autoclave bonding looks like that outside, and it's a process in which a part is cured in an autoclave, and after you do your layup or winding. So the autoclave is just a heated, okay, and is a vessel, kind of like for pressure, yeah, pressurized vessel. So this process allows the complex curing reaction to happen in there. So the additional pressure allows a higher density and then improved removal of all that unwanted volatiles from the plastic. So the drawback of this process is a high investment cost because autoclave machine is very expensive, and since it is a pressure vessel, it must follow the strict pressure code regulations. Okay, also the government regulations, especially the quality crew, having to issue all the time because they have to protect the machine because it's very expensive. So therefore, the regulations are strict. So meetings regulation results in expensive piece of that equipment. Yeah, because quality system and you have to hire the consultant. You usually don't have anybody to do that regularly, and because it's too expensive to pay a quality executive or what can I say, like the higher level management. Occasionally, you have to pay a lot of money, and they cheat by not hiring the quality folks in a higher level or upper management. Okay, they usually keep quality folks up to like middle management, but then they will, okay, because it's too expensive to keep a person like that, because they've got to calculate all the time. So what they do is just let things go, all right, and hire the quality consultant from the outside just for a short period of time and pay heavy, okay, at that period to solve all that, pass that regulation stuff, pass the quality, okay, assurance stuff, government stuff. So anyway, so let's go right to here is a textbook picture. It's the same thing. You can see your large autoclave system right there. Autoclave system is another machine, the same thing that you can see. So we have the vessel, and then we have a heated pressurized gas stream, okay, and they vacuum the source inside of that machine. So the vessel is where the part is placed and then contains that pressure. And the heated pressurized gas is circulated uniformly within that machine or vessel. So an inner gas, again, is typically used to reduce the danger of fire. That's why we have nitrogen, okay? Nitrogen is the highest percentage in the air, because without that, okay, our world is going to be on fire. We can live like this in this safe, okay, atmosphere in the world because of the percentage of nitrogen, which is the inner gas. Again, what you need to know is inner gas usually protect us from the danger of fire. Okay, so an inner gas inside of this machine is going to reduce the danger of fire. So the vacant source compresses the layers of the composites, and it has a control system, the same thing. So every machine has a control system for the temperature, yeah. So operating parameters, so that's your pressure, temperature, and everything that you need to control, it's in there. And this system also has automated part loading and unloading function, okay. It's a pressurized compartment dealing with the different temperatures, therefore you need an automated loading and unloading function. It's really helpful. Otherwise you have to wear your glove and take it in and take it out, right? It's just too tedious to do that. Pultrusion. Pultrusion is another method. So this process for making, okay, continuous length or reinforcement composite structure shapes, and it looks like that. Okay, as your production line right there. So spindles or crease hold the reinforcement for feeding into the guides, and resin bond again saturates or wets out the reinforcement with a solution containing the resin, filler, pigment, your catalyst, your accelerator, and other required additives. And on exiting, okay, that resin part the composite is in a fleshy form. So then the composite is passed, okay, by the preform. So here we're going from here all the way to here. So that's your preform right there. And here is your continuous stand your guide plate. Okay, so here we start feeding into the guides. So here is, you can see the arrows are going that direction. Okay. Alright, then we get to the next step, a preform. Here you go, is an array of tooling that squeezes away the excess resin and gently shapes the material before entering the die. Okay, now here is your die cavity right there. So in the die, the thermoset reaction is activated by the heat. So every time you shape, you need the heat to melt the plastic. So the composite is then allowed to harden and cure. Then you have to make it hard by controlling the temperature to set that plastic that's been molded, and then the part must be cool before it is gripped by the pull block and removed from the die. Okay, so go in this direction. So this is to prevent cracking and also deformation by the pull blocks. So after exiting that die right there, the cure profile is cut. Okay, and this is your pulling the product out of the die, and then here is your cut. Cut station right there, and you're going to cut over the saw in this case, okay, to shape the products. So I think you get the idea. So the first slide go from here to there, and second slide from preform to the end. This is your textbook picture for pultrusion, and it's just showing you it involves the pulling reinforcement through a resin, okay, and heated die. And you can see your guide is right there, your resin. This is where you saturate the resin, and then we have self-facing material right there, and here is your preform, okay, and this is your die, right? This is where you form with your heat, your temperature controls everything there, and then you're going to pull it out and then cut, okay. So this is just a two-dimensional, starting from your roving creates all the way to the cut saw. Compression molding. So it's one of the oldest manufacturing technique in the plastic industry, and you have already learned about that in plastic unit and then chapter. Okay, and traditionally it has been used for molding relevant compounds, and then your thermoset powders. So thermoset powders, your phenolic and your alkyd. So it's performed simple tools at low pressure. So also very little material is wasted in compression molding. Everyone like that, and that's why it's one of the oldest material. And high quality of fibers and long fibers can be handled easily in this molding. So better physical and mechanical properties can be achieved in molded parts, and the steps in the process can charge preparation and placement, mold closing, and curing. So this is just a review for your compression molding. I don't have to brag about it again, okay? So you better review that and go little by little. I'm not looking for you writing all that back to me, okay? I'm looking for you understanding it and reproduce it in your own words, yeah? Like you talk to somebody. This is your diagram from your textbook. So you can see right here in the typical compression molding process, and charges are cut and then placed in the mold right there. Okay, so here that's your first half of the mold, and then this is your second half of the mold because you're going to compress in that direction. So then the mold is closed. When you close, you're compressing it, compressing the part, and then you're going to open it, okay, to release the part. So here is your charge. Charge means it's a material to be molded, and here is your injection pin, right? Ejection pin right there, and that's your fixed platen, and movable platen is the one that's going to mold this charge, okay, into shape. Okay, since we're going to do the molding, we're going to prepare the charge. So charge preparation and then charge placement in the mold. So the stack of the sheet molding compound is placed in a preheated mold. You're going to heat it. Heat is important in making shapes, okay? So the stack of sheet is called the charge. So the sheets are first die cut. So here we know it's talking about a stack of sheet. So your charge raw material is in the form of the sheet, and all you have to do is just stack it up. Yeah. So a stack of sheet is called a charge, and the sheets are first die cut into the desired sheet and sized according to the product course, and then they're then stacked into a charge outside the mold. And then the charge weight is measured. You need it because that's essential for shaping everything. And then just before it is placed into the mold, the charge is then placed in the mold. The charge location in the mold is the key factor in determining the quality of the mold part. Okay, and then the location influences fiber orientation. Again, don't forget how important the fiber orientation is for the strength of the shaped material. Yeah, porosity and other defects, and the final property of that composite. So here you can see the charge in the lower fixer mold, and that's the upper movable mold is going to be held right there when you're preparing your charge. And then we're going to close. So mold closing. So after the charge has been placed in the bottom mold, the top mold is moved down quickly. Press it, okay, until it contracts the top surface of the charge. You're compressing it now, and then the top mold is closed at a slower rate. Go slow. You need a slow pressure to shape, right? Shape the charge or product. So as temperature in the charge rises, the viscosity of the sheet molding compound is reduced. So as the mold continues to close slowly and increase the pressure, right, because this is going to press, the sheet molding compound flows to the cavity extremities. Now we're shaping it. Yes. So and this forces air in the cavity to escape out. And air is going to come out from here. Yeah, we don't want any air, we want all of that out. And then we're going to press it out. Curing, we're going to set it. So after shaping it, so after the cavity has been filled, the mold remains closed for a time. Yeah, it depends on what you're making. So that, again, even though it's so easy to write it here, you have to pay attention when you're actually making it, yeah, to assure the reasonable level of curing. Of course, you will always have a standard deviation, plus or minus, shine, some temperatures away, up and down, yeah. Lower curing imply consolidation through the part. So why do we have to do it? We want the quality. Okay, we want to maintain the quality of the product. So this step is so important in quality assurance. So the curing time may vary from 1 to several minutes. So the amount of time depends on several factors, including the resin catalyst, inhibitor reactivity, part thickness, and mold temperature. So the end of the curing, the top mold, we're going to open it, and then the part, we're going to remove it from the bottom mold. Yeah. So there is a piston to raise it up, so you can get your shaped product out of the mold. Otherwise, this piston is so important to lift it up. Okay, so it's going this direction. You can see the speed. Again, to put that speed is also really important, so that you're not going to D-shape, right? The product. We want a perfect product. So the speed right here is not like whatever speed. This is the speed. And you want to go to slowly raise it up, okay, and then mold it apart. So at the end of the curing, the top mold is open, the part is removed from the bottom mold, and the part is allowed to cool outside, okay. Then the mold is then prepared for the next part. Pretty easy, yeah? Easy to talk about, but very difficult to do outside, by the way. You have to be so careful. That's why we use the automated system and put the responsibility on the machine. So anyway, the sheet molding compound, SMC. Sheet molding compound is a continuous sheet of ready-to-mold composite material, and then it contains the fibers and the mineral fillers dispersed in a Thermoset resin. So SMC is cured and then transformed into a finished product by compression molding. Okay. It's about the same thing, but the material now we use it instead of the charge, we're using a sheet. So the major components of FNC are we have your resin, and then we have the fibers, and then we have the fillers. And the other components are used in small quantities, like our accelerator, catalyst, thickener, okay, to increase the density, and then inhibitor and mold release agent to come up with the fine finished product. Mold release agent is necessary, and low profile additives. Okay, why these agents are used is because when you release the mold, sometimes it's a mess up. Yeah. So advantages of SMC composites are variety, part consolidation, lightweight, and dimensional stability. Yeah. That's a little bit difficult to see right here, but then I don't want you to get the whole thing, just trying to understand that it's a sheet feeder. Yeah. And here's a table showing you the composition of a typical sheet molding compound. So here you have your material, the resin paste, and this is in fiber. Fiber is mostly glossy anyway. And here's amount and weight percent. Yeah. And then another textbook diagram showing you the sheet molding compound production in 2 dimensions. And we're doing it by chopping the glass fibers. Okay, so here you can see the chopper over. Here is a continuous strand coming into this roving, and then here is your carrier film roll going that way, and here is your resin paste right there. Okay, here is your chopped fibers coming down, and here also the resin paste right there, and here is another your carrier film roll. And these are your compaction roller. It just pull you are just rolling. Okay, your take up roll is that way. So this one, in this case, and this from the textbook, just using polyethylene, okay, for your resin, and to which the resin paste mixture has been applied. Okay. And here I'm trying to point out the second time again for where the resin paste is. Injection molding. A molten polymer is injected into a closed mold, and I have already taught you the injection molding, and you can be able to remember the cartoon. Okay, this one is a real life machine outside. So the polymer solidifies in the mold, taking the shape of the mold cavity. So your die cavity is around here, okay, and your screw and your motor is right there. And here is your feeder. So the mold is then opened and the part is ejected and then removed from this side. So the thermosets are used in injection molding. So I don't have to tell you again, just review your previous chapters. And thermoplastics, these composites come in filled reinforced form, so which means that a discontinuous and rigid phase has been blended into the polymer. So they're just trying to say that the thermoplastic composites are better than the thermoplastic itself, is because they're already processed. Okay, that's what it's telling you about in the first statement. And then reinforcing materials can be either, it can be fiber or flake. So most thermoplastic composites are made in 2 steps. One is a compounding and the other one is cutting. What's compounding? So fibers, fillers, we're going to mix them, so blend it into molten resin. So since it is molten, we have temperature control using an extruder screw. Okay, usually connected to a motor to mobilize that. Cutting is extruded, compound is cut or made into pellets for further injection molding. Okay, this is just making raw materials, so what's trying to tell you about that. Thermoset plastic molding compounds are in the form of pellets or granules. So they are alloys, your aminodes, your epoxies, and phenolics. Thermoset polyesters and thermoset polyimines and polyimides and silicones. So similar process of making composites are in thermoplastic composites. So because of their 3-dimensional network structure, they have excellent mechanical properties. They have good heat resistance and chemical resistance. So why do they have those kind of properties? Because they have 3-dimensional network structure. Again, structure matters for whatever properties you have and we can perceive outside. So therefore they can retain their performance characters, dimensional stability at elevated temperature, and preferred over thermoplastic in some applications. Okay, so meaning like we use the thermoset more than the thermoplastic, and you have already studied that. Right? The percentage is heavier in thermoplastic applications. So resin transfer molding is your RTM But you always see the RTM, that's your resin transfer molding. And here's a diagram to show you, so you can be able to see it. So it has developed from the conventional reaction injection molding. Okay, same as that process. So a mold is, you're going to load it with the reinforcement material, because we're dealing with the composite, yeah, before the resin is injected into the mold. So the mold is often subjected to vacuum, right, to remove the trapped air from the reinforcement. Okay, so the reinforcement material is wetted by the pressure of the injection. Okay, so this going the same way again. So here you have your first step, and then go perform injection mold right here. You're going to close the mold. Okay, and here we are exerting the pressures, raise injections happening right here in this step. And we're going to remove the part from the mold, and you have your finished part. Okay, and here is just a preparation for this method. And that's your reinforcement putting into this composite. So here's your textbook diagram. So in resin transfer molding, RTM, resins are injected slowly into a mold in which reinforcement has been loaded. Okay, so here resin injection machine. 2 dimensions are a little bit difficult to read it. Okay, you're going to put A and B, and the resin is going to go in. These are just a raw material that you're feeding into the machines. And here is your mold, and you're going to mold the part, right, using the pressure right there. Pressure comes from your clamping press on both sides. You have bottom and you have top, and we're going to take the air out because we don't want these volatiles, and that's how you make the part. Yeah. So reinforcement, what kind of reinforcement do we use in RTM? So we use gloss, we use carbon, we use aramid fibers, in addition to the standard reinforcements. So the material must retain its shape during the subsequent injection. So therefore reinforcements are stitched or bonded together. And then the preforms, okay, preforms are commonly used. Preforms looks like that. And screw receptacles, ribs, inserts are placed in the open mold, while fiber reinforcements are placed into the matrix. Okay. Of course, it's not so important. And what's important is right here. Yeah. And here, this is the gloss, carbon, and especially the aramid fibers are very commonly used in RTM. So at least you have to get this. Yeah, the first statement. Okay, so resins for RTM. So what kind of resins do we use? The polymer resins. We use a polyester and an epoxy. So slow injection is used because everything that you've got to do with the mold, you have to control the pressure to shape it into a good product. Okay, so slow injection is used for a good wetting of your reinforcement. And then the resin pot life again should have about 2 hours. So don't forget the pot life. You know, that's when your inhibitor is added for the polymer reaction, okay, in the resin system. So about 2 hours that need to slow the injection without forming the resin gel, because we don't want to mess up. So therefore you take time, okay, to do the injection. Okay, try it. You can't do the injection so fast. If you do the injection so fast, you get a mess. Alright, so mold for RTM. So the design of mold is critical in RTM because the mold is the one that is going to shape the product. So if you want a sophisticated, important products, okay, costly products, then you have to come up with your design for that mold perfect. Yeah. So the mold is made for resin to reach all areas. Because if the resin is not going to flow to all areas, your product will get defects. And to keep the even resin concentration throughout, so the resin movement must be completed within the time allowed before curing. And then the injection process should not move the reinforcement. Okay, they're all important steps, by the way, very important. You can forget about it, right, in academic settings, but when you go and work, you have to follow each step very, very, very carefully. Okay, whether you're in the setup or whether you're in the observations or whether you're in operations, okay, or process. You must strictly follow to come up with the quality products. So the mold must maintain the shape of the reinforcement during the injection. So the mold must be vented to allow air within the mold to escape. And then the vent should be small enough not to let the resin flow out. We only want the air out. You don't want the whole resin to spill out. So the mold also needs a proper temperature control to optimize the resin temperature. Okay, resin curing to set it properly. Properties and applications, what are we using? So properties depends on the type of matrix, type of reinforcement, concentration, form, distribution, and orientation. Okay, don't forget the orientation of the fibers, because that's will determine the strength. So thermoplastic matrix composites, thermoset matrix composites, high temperature thermoset matrix composite. We have different types for thermosets. We have high strength, medium temperature thermoset matrix composite. And don't forget, this is a multi-cycle heat cycle. Thermoset, you have to be so careful for the temperature, okay? It's because it can go only one heat cycle. Then we have a medium temperature thermoset matrix composites, okay? Alright, so thermoplastic matrix composite, so the properties differ significantly with the fiber length. So we have long fiber and we have short fiber. So the fiber length considers our long fiber reinforced. So that's a 0-degree orientation. And we have a short fiber reinforced, your mixed, okay, fiber, short fibers in the matrix, and then unreinforced, so there's no reinforcement. So properties considered are your tensile strength, the flexural strength, and then your modulus, and then you have, this one depends on your density, and then your heat distortion temperature and your impact strength. So here it's showing you all of that, okay, tensile, flexure, modulus, the heat distortion, and impact strength according to the different reinforcement. So we have unreinforced, the black ones, short fiber, this guy, and a long fiber. So when you look at it, you see the long fiber seems to be better for all dust quality. Okay, so this will be your favorite choice. Alright, and this one is the padlocks, and these padlocks are made from polypropylene composite filled with a long glass fiber reinforcement, so therefore very strong. Yeah, that's what we're using for lock. Okay, you can go and burn it. So some thief, or if you want to vandalize somebody or rob somebody, then you can try to burn this one with some acids or something. Not the fire acids. Okay. Okay, let's go. Thermoset matrix composite. I shouldn't tell you all of that. Oh my gosh. Alright, so thermoset matrix composites. So these composites have a superior stability and mechanical property. So thermoset matrix composites are these things. Okay, I already show you they have a different temperature. Again, temperature. Okay, control for thermoset. Why? Because these composites, they have superior stability and mechanical properties. Okay, how strong they look at that. So high temperature thermoset matrix composite, polyimide typically used for the composite. The resin can be used 600 all the way to 900 for short period, 600 for long duration. And then the composite, they have excellent electrical properties as well. Major application we're going to use in aerospace and electrical industries. Okay. The high strength, medium temperature thermoset matrix composite. So epoxy resin systems are typically used where high strength is required at medium temperature. So what we're doing, glass, carbon, graphite, quartz, aramide fibers are used in the molding compounds. This is just making a floor, okay, a type of floor from the thermoset matrix. And some reinforcement, you can see the orange, how shining that is. A high layouts and fiber fabric, prepreg your fabric, composite for various applications. Okay, so the mechanical strength of epoxy composites decreases with increasing temperature. So you have your regular concrete, and then over that we're using the plastic, which is your thermoset matrix composite, okay, to complete the floor. Okay. So this is kind of like building and construction, like important building, like your department stores, okay? Your skyscrapers, your high-end condominiums, and millions and millions of dollars of houses, okay? So go with a shiny floor like that. Medium temperature thermoset matrix. So phenolic resin systems are typically used for medium temperature thermoset matrix composites. The resins are usually saturated with glass again, carbon, and graphite cloth. So they're used for tape wrapping or handling up aerospace components, okay, rocket nozzle, and the insulation liners. So here you can see making another floor, but this time we're using the medium temperature thermoset matrix composite to finish the floor. Okay, so here's doing the manual layout right now. So the material strength of glass, cloth, fabric, phenolic, thermoset composite decrease, okay, with increasing temperature. So you definitely need to again control the temperature to get the right, okay, strength. If you mess up the temperature, you're going to be messing up the tensile strength of that material. Okay, so low temperature thermoset matrix composite. Thermoset polyester resin are widely used for low temperature applications, usually in construction. So thermoset polyester composites are widely used in transportation, construction, electrical, consumer, and consumer products. Okay. So a typical applications of glass fiber reinforced polyester composites is like this in construction of a structure. So here you can see these are all thermoset composite. Okay. Or it looks like a gym or a stadium kind of thing. And here you can see another structure. So this is the 3-story turrets, and they have constructed that with the polyester fiberglass composite, and they're housing communication equipment on top of the Sunbank building in Orlando, Florida, down there. Okay, so we can go when you go to Orlando and try to pay attention to Sunbank or whatever that structure or building, and you can take a look at that. And it is made of polyester fiberglass composite, your plastic composite. Okay, so that's the end of our Unit 9. Unit 9 is a pretty big thing, but then it's not difficult. Okay, just go slow. Try to get like maybe 10 slides. Okay, so there are 3 parts, and this one is like a 51 slides right in there, so you can run about 3 times on that video. Don't skip the lecture videos, okay, because the important points are right in there. Even though we ask you the easy questions at the end of the chapters, what you really have to do is to be able to understand all of that material in the easiest way, okay? And I'm giving you that information in my lectures. Things that you really need to know when you go out. So you will be familiar with all that terms, processes, okay? And you can picture what they are, especially, manufacturing environment, okay? Alright, so I'm going to go ahead and stop right here.